heat conduction last time as the first part of heat transfer chapter. So we will be continuing ahead with that today. And just to clarify, your test coming up on Sunday, the portion will be up to heat conduction. The last part of heat transfer, which is to do with radiation, will be excluded from the test because we will not be able to cover that up to the test. Okay. So let's begin with a quick recap of the concept of a thermal conduction or heat conductor happening in steady state. Okay. So I'll quickly recap that concept that we were discussing about the previous lecture. So we saw that if we have what is called an isotropic heat conductor, like for example, it could be a metallic rod with a uniform thermal conductivity, which we denote with the symbol K. And it's of length L and cross-sectional area E. Now, if we insulate it from the outside, okay, and just keep the two ends of the metallic rod in two separate temperature reservoirs, one having a high temperature of T1 and the other reservoir having a low temperature of T2, then what will happen is heat will flow only along the length of the rod. And we saw that in steady state, the rate of heat flow that becomes this particular quantity. And also apart from this, there is a uniform temperature gradient. Okay, so the temperature versus position, if we take position inside as at a distance x, this becomes a linear graph ranging from T1 to T2 as position ranges from 0 to n. Okay, so these were the two important properties of a conductor in steady state that we had learned in the last lecture. Okay, now today we'll begin by an important related concept, that the concept of thermal resistance and heat current. Okay. So this process of heat conduction through a conductor at steady state can be treated like conduction process where the temperature difference between the two ends plays the same role as potential difference in the case of electrical conduction. So the heat current is equal to the temperature difference divided by thermal resistance. Okay. Just like for a regular resistor, we apply a potential difference, then the electrical current is equal to V1 minus V2 divided by electrical resistance. This is Ohm's law. This is the electric current. And this is the electrical resistance. Now, if you compare this, you can see this is rho L by A, which is the same thing as L upon sigma A, where sigma is electrical conductivity. So in this formula, you can see that basically it's delta Q by delta T, which is Ka by L into T1 minus T2. So by comparison, you can see that the heat current is the rate of heat flow, whereas electrical current was the rate of charge flow, and the thermal resistance is L upon Ka, which is analogous to this formula, that electrical resistance is L upon sigma A. Okay, so that is how we understand this process of thermal conduction, like a current flowing, but only the current flowing here is a heat current, and the resistance we are talking about is the thermal resistance. So this helps us solve problems where there is combination of heat conductors creating heat current. Okay, so now we can use this concept in any combination of conductors. Directly and reduce the problem to an equivalent circuit problem. For example, the type of question we did in the last lecture. So if we pick up something like that, we have, let us say, two heat conductors which are placed end to end in contact like this. So this is having some thermal conductivity K2, length L2, area A2, and this is in contact with another metal having conductivity K1, length L1, area A1, and we are maintaining the temperatures at T1 and T2. Also, we have created some kind of insulation from outside. So now we want to find out the net rate of heat conduction. Okay. And we want to find out the temperature of the junction. Okay. So what we can do is, in this type of problem, we can convert this to a series combination of resistors. But only these are thermal resistors. So at the end of it, we have temperatures T1 and T2 and a heat current flowing through like this. And suppose this temperature here is unknown. So this becomes equivalent to this, which is R1 plus R2. Okay. So delta Q by delta T net is this heat current, which is this, where R equivalent, as you know, in a series combination is this. Okay. And T1 minus T by R1 is equal to this heat current. So from this we can find out T1. So this is an example of series combination. Okay, now similarly, let's see the parallel combination. Oh, yes, yes, that's correct, Vaishnavi. People, important correction here. Just I've taken the case where even the areas are different. So it is L1 upon K1 A1 and L2 upon K2 A2. Okay, so just make this small correction here. The areas for the two conductors, the area of cross section is also different. So R1 is L1 upon K1 A1 and R2 is L2 upon K2 A2. So you should understand this here. Yeah. So thanks for pointing that out. And accordingly, we have to just substitute these here and get the answer. Okay. So make sure
So,
you.
sir, how did we get the last equation?
Sorry, beta.
So, the last equation, T1 minus T
Last
upon.
equation कैसे है ना? Okay, see this one, na? This equation,
Yes,
right?
sir.
So we have to apply the Ohm's law across the resistor R1 in the top diagram. So across this resistor, how much is the temperature difference? T1 minus T.
Yes, sir.
That temperature difference divided by its resistance is the current through that conductor. Now the current through that conductor is the same as the equivalent current. So we have got equivalent current from the first one. No? Now we will substitute this in the second one. So we will find
Okay,
out
sir.
this IH in the first one and then substitute this in the second one. So from that, this T will be, sorry, we'll get the T. T1 is known to us, but T is the unknown one. That is the temperature of the junction. Okay. So temperature of the junction, the unknown quantity we'll get now. Okay.
Okay, sir, got it.
So we are assuming that all these things given in the diagram are known to us. So T1, T2, L1, L2, A1, A2, K1, K2. These are all known to us. Okay. So now on the basis of these known quantities, we have to find out these two unknowns. So that first one we are getting from this equation, second one we are getting from second equation. Okay, we'll do some example problems, so don't worry, you'll get used to this. But before we come to examples of combinations, let's look at the second type of combination, which all of you know, parallel combination. Same thing that you have seen in electrical resistors in combinations in class 10th. Okay, so it's like a revision of that concept here actually. So anyhow, so if we have this kind of a situation now, for some reason, let's say we have created two heat reservoirs or temperature reservoirs, and across them we have connected two rods or two metallic conductors, but in parallel instead of in series. So that would look something like this. This is a temperature reservoir at T1. This is a temperature reservoir at T2. But now the conductors we have connected are like this. They are parallel to each other. So in my example, geometrically it is such that they would have to have the same length. But even that is not absolutely necessary. So they, in this case, they are having the same length, but that's not necessary. The shape of the thing could be such that L1 and L2 are also different, but they are having different areas and they could be made of different materials. So this is K1 and this is K2. So now what will be happening is that there will be some heat current going through this one. There will be some heat current going through this one. And the net heat current, delta Q by delta T net, that is the net current, will be I1 plus I2. So in this case, this will become T1 minus T2 by R1 plus T1 minus T2 by R2, which is T1 minus T2 by equivalent resistance. Okay. So this thing will become our delta Q by delta T net. Okay. Where now comparing this equation with this equation, this whole equation with this one, you can see that you get the standard formula that sum of reciprocals is the equivalent reciprocal. So where 1 upon equivalent resistance, that is reciprocal of equivalent, is sum of the reciprocals. So this will become K1, K1, or in this case the L is common, but it could be different also. So this becomes the equivalent resistance. So the equivalent circuit for this is that you have two combination of resistors which are connected across the same temperature difference, two heat resistors. So this net current is getting divided into two branches. So obviously in questions you will have a situation where you have to use both of the concepts put together in the same combination. Some of the resistors will be in series, some will be in parallel, and we have to find the equivalent resistance and things like that. R1 is not equal to R2 beta. Lengths are equal. R1 is not necessarily equal to R2. It can be equal to if it's designed in that way. And if R1 is equal to R2, then I1 will be equal to I2. So each of the branches will have half the total current. Understanding, Naman? K is this thing, no, it's thermal conductivity. Okay. So the electrical resistivity is the inverse of electrical conductivity. It's 1 by sigma. But this sigma over here is electrical conductivity, whereas K over here is thermal conductivity. So there are two different material properties. One is to do with how the metal or heat conductor conducts heat, and the other two is to do with how the metal or electrical conductor conducts electricity under voltage difference. No, Ansh, it is not necessary always that in parallel the lengths will be equal. The type of shape I have drawn, it was necessary here that the lengths are equal. But the heat reservoirs can be shaped in a different way, no? So that the two interfaces are not parallel to each other. So in that case, the lengths could be different. So in that case, when you do 1 by R1 plus 1 by R2, you'll have different values of L1 and L2 in that formula. Okay, so let's look at a typical example question next. So we now have an entire network of resistors or thermal resistors, let's say like this. So these are three of them, and they are combined with another three of them, which are like this, let's say. Okay. So let's say these three have thermal conductivity K2, and these three have thermal conductivities K1. And also these all have length L. Whereas this has length L by 2. Okay. So given that K2 is equal to twice of K1 and K1 is equal to, let's say, 240 watts per meter Kelvin. Oh, before I come to this question, let's just go back for a minute to the basics and understand the unit of thermal resistance. Okay, so just a moment. Coming back here, so let's just add this point. Unit, SI unit of thermal resistance. it is Kelvin per watt. So when we use this formula, in this L should be in meters, K should be in watts per meter Kelvin, and area should be in meters square. So then thermal resistance comes in Kelvin per watt. Okay, so just make sure you are aware of the units here. Okay, so let's come back to this question now.
So can you please scroll up?
Yeah, I'll scroll down.
Done, sir.
Yeah, so now coming back to this, so this is additionally what is given to us. Now all the rods have same area of cross section. Which is 6 centimeters square. Okay. Now this end is P and this end is Q and this point here is S. Okay. And assume there is some insulation everywhere. So like for electrical wires, we have some non-conducting shielding, like some plastic shielding or rubber shielding. Like that for thermal conductors, we have some kind of thermal insulation from outside. Okay. So what's happening in this example is a combination of 6 metallic rods are arranged as shown. Okay. And ends P and Q are maintained at constant temperatures. T1 equal to, let's say, 150 degrees C and T2 equal to minus 50 degrees C. So first of all, find the equivalent thermal resistance across PQ and find the net delta Q by delta T at steady state, and also we have to find the temperature of the point S at steady state. Okay. So this problem is like a good workout example for any circuit problem, whether it's an electrical circuit or thermal circuit, whatever be the case. Kevin, you want me to zoom in, but the whole screen is there, I think. Is it okay now?
No, sir, I was telling to zoom and not zoom out.
You want me to zoom out?
No, no, yes.
Okay, okay. Just a moment. Yeah, I'll show you the rest of the question. Okay, so what we have to do now, we have to convert this to an equivalent circuit. That will be the easiest way of solving. And find the equivalent resistance, then find the net current, and then solve like the equivalent of Ohm's law for certain branches of the circuit, from which we can find out the unknown temperature of the point S. S is this corner point on top. The top right corner point of that box is S. So that corner point's temperature we have to find at steady state. So just like you would do for an electrical circuit to find the unknown voltage at a point or to find the potential difference across a rod or something like that. Same kind of method will apply here. Okay, so anybody got the answer yet? Let's try to figure this out. Okay, okay. So what I'll just do is I'll start with converting this to an equivalent circuit. So that would be like 3 of these resistors. Okay. Then one of this resistor. 2 of these resistors. Okay. Yeah, formula you have shown is correct, Sangeeta. Okay, so let me just elaborate the method, the exact value now. So next step, what we will do is we will take these 3 in series combination. So that will become, let's say, R prime, which we can write as R1 plus 2R3. Okay. So this will become, so next what we will do is we'll take the parallel combination of these two. Okay. So let's say this is R double prime. So that will become 3 by 2 into half upon 3 by 2 plus half. 3/4 divided by 2. So this will come out to be 3/8 R1. So finally, now my R equivalent will become R1 plus R double prime plus R1. So nearly 40 equivalent resistance. I'm getting nearly 40. And just check my solution.
33.
Oh, sorry, nearly 33. My mistake. Yeah. All right. So now my equivalent current. Okay, that will be the same as the current in this. So the net current is nearly 6 volts. This is approximate value, but it's more like 200 upon 32.99. That's approximately equal to this. Okay, now the only thing remaining is we have to find the temperature at that corner point. So I'll come to that. But note this down first. Jenny, we have to convert both the temperatures now. So see, first of all, if we say thermal resistance is X number of Kelvin per watt, okay, this is the same thing as, okay, so this thermal resistance is equal to what? Temperature difference divided by thermal current. So temperature difference is in Kelvin and this is in watts. So temperature difference in Kelvin is the same thing as temperature difference in degrees. Got it, no? Yeah. So either I have to convert both T1 and T2 into Kelvin and then subtract, or I let them be in degrees C. But this is the delta T, which is in Kelvin or degrees. It's one in the same thing. Because it's a delta T, not an absolute temperature, it's a change in temperature. Okay, now we have to find the temperature of which point? We have to find the temperature at this corner point. So let's come to that thing next. So we want to find the temperature at this corner point. So third part of the question. Okay. So for that, see, we will concentrate on this circuit diagram. So I'm just taking this below. Anyhow, so this temperature I want to find out. Now I know this current. This was the net current, and this coming back here. Okay. And I can also calculate. Suppose this current is I1, and this current is I2. Okay. So we had also seen that this was equivalent to R prime. This, so So I net I know now. Okay, I net's value is 200 upon 33.9 or approximately, so 32.9 or approximately,
6 watt.
yeah, that one. So 6 watts, approximately 6 watts. Okay, so I know that, and I also know that this R prime, this was how much? This was 3 by 2 R1, and this R2 was R1 by 2. Okay, so now in this circuit, if you concentrate here, I net is the sum of I1 and I2. Okay, and R prime into I1 is equal to R2 into I2. Okay, or I1 is to I2 is equal to R2 is to R1, which means that in this case, I1 is to I2 is 1 is to 3. Is correct? All right. So from these two equations, now I can conclude what? I can conclude that I1 is 1/4 of I net. Okay. So it is almost 1.5 watts. Okay. Now let us name this point here as something else. Let's say T or whatever H. This point is already this. So see, the current going through this resistor is I1, and the current going through this resistor. So now we'll apply for HQ. We will apply temperature at H minus temperature at Q should be equal to I net into R1. So from this we'll get the temperature at H. So temperature at Q was minus 50. So this upon R1 should be equal to I net. Now I net, if you remember, was T1 minus T2 upon R equivalent. Okay. So TH my plus 50 upon R1 is equal to 200 upon, and how much was R equivalent in terms of R1? If you just do that calculation, R equivalent in terms of R1 was 19 by 8 times R1. That's an even more convenient way of doing the calculation. So temperature at H will become 200 into 8 by 19 minus 50. That I can write as 50 into 32 by 19 minus 1. That is 50 into 13 by 19. This is the temperature at the point H. Now next thing, apply the same Ohm's law to SH. So temperature at S minus temperature at H divided by R3 is equal to I1. Okay. So temperature at S minus temperature at H divided by R3, which was R1 by 4, is equal to I1. Okay. Now I1 is how much? I1 is from above 1/4 of I net. And I net we just saw is 200 divided by 19 by 8 times R1. So TS will become TH plus, now this will become 200 16, so 2 into 19. So this should be TH plus 100 by 19. So this temperature will be about 39.5 degrees C. Okay, so this is what we get finally. So the thing is, you have to be prepared to have the patience to do a calculation like this through. But rest it's pretty easy. It's just usage of Ohm's law repeatedly and the concept of equivalent circuits. Acha Vaishnavi, that came from the fact that you'll remember that in this diagram, now this R3, in the first diagram, see in this diagram, for the branch SH, the resistance R3, that was how much? R3 was L by 2 divided by K2A. And this K2 was equal to 2 times K1. So R3 became L upon 4 K1A. So that's how I got that. So might have just missed this out. This was in the first part that we had solved.
Sir, I was actually asking that R1 by 4, that 4 was multiplied in the numerator or not, because that step you didn't write. So
This one, हाँ यहाँ पे multiply हो गया ना. See, that's how this 8 in the denominator went away ना. See, this TS minus TH is becoming, this 1 by 4 is coming to this side. So 1 by 4 into 1 by 4 into 200 divided by 19 by 8. So that's how this is becoming 200 by 2 into 19 or 100 by 19. Is it all right?
okay, sir.
ठीक है ना, it's numerically correct. Just check the step once. I have just done the calculation in a hurry. Okay, so basically you can get any sort of combination of conductors like this, in which you can convert the given combination of metallic rods or heat conductors into an equivalent circuit diagram and just apply the normal principles. Like over here, when we have equated I1 plus I2 equal to I net, we have applied conservation of current, or what is called the junction rule, that at a junction, the total incoming current is equal to the total outgoing current. At rest, we have applied the equivalent of Ohm's law, that delta V upon resistance is equal to current. So instead of delta V, we have temperature difference divided by thermal resistance is equal to heat current. Okay, so hope this question is done, right? We'll move ahead now. Okay, let's understand that. Okay, this is so this is R prime. You can see the earlier step, no? This potential difference is equal to this potential difference. Okay, so that is why I1 into R prime should be equal to I2 into R2. So this should be R prime, and that you can see is R2 is how much? R2 is R1 by 2 is to R prime, which is 3R1 by 2. Okay, so basically this upper resistor and this lower resistor, they are in 3:1 ratio. So the currents will be in 1:3 ratio. Okay, yes. So just make that small correction here. I'd written this R1 by mistake. This should be R prime because it's coming from this step. Okay, now next we will move on to a situation where we are dealing with we are dealing with thermal resistance of anisotropic conductors. That means the material is anisotropic, it's not uniform everywhere. So we have to use definite integration. So this becomes by application of definite integration. Okay. So for example, suppose we have a situation where we have made a metallic rod with some kind of alloy of two metals, but the mixture of the alloys is not uniform. So it's the way the two metals are mixed in percentage composition that is not uniform everywhere. So it's an anisotropic, or that means it is non-uniform in physical properties or in material properties, metal rod. And it has length L and area of cross section E. But also it is given to us that inside the metal, it is given that the thermal conductivity varies with position x such that K is equal to K naught 1 plus x by L. So this is given in the question, okay, that the material we have designed is such that as you go from the left end of the rod to the right end of the rod, the thermal conductivity varies from K naught to 2 K naught, where K naught is a constant and L is the length of the rod. X is the position at a point inside with respect to the left end of the rod. Okay. So you want to find the thermal resistance for heat flow along its length. Okay. So that means if we subject this rod to that kind of situation where heat is flowing along the x-axis, so we've insulated it from outside and kept the left end and right end at two different temperatures, then at steady state, how much is the heat current? And from that we can measure the thermal resistance. So here, instead of doing the measurement of thermal resistance with an actual experiment, we will calculate it theoretically by using differential calculus, or rather by using integral calculus. Okay. So the thing is that here we cannot use the formula that thermal resistance is equal to L upon Ka. We can't use this because K is non-uniform. Okay. So instead what we understand, K is a function of X. Therefore, we have to take a thin slice, okay, or what we call a differential section, like you do in calculation of moment of inertia or center of mass, a differential section of thickness dx of the rod. Okay. And first talk about the thermal resistance of that section, and then from that we will understand what is the total thermal resistance of the entire rod. Okay. So just make a quick note of the things given in the question, then we will discuss further the application of integration. So by now you will be getting more and more used to the application of integration. You have seen it in center of mass, you have seen it in moment of inertia calculations, this kind of geometrical integration. Okay, so let's understand what we'll do here. So keep in mind that heat is flowing along the length of the rod. The heat current is along the length of the rod. And in steady state, there is uniform heat current everywhere. Okay. Because we are maintaining a temperature difference T1 minus T2. So now if we cut an arbitrary differential section, just a yeah, so students, coming back to this, so if we take arbitrarily at a distance x from this end, if we cut a section of the rod, so if it's, let's say, a cylindrical rod, so we have cut a section of this cylindrical rod, of thickness dx. So this differential section, the heat is passing through its thickness. So it has a thermal resistance of dx upon Ka. So that is dx upon K naught 1 plus x by L into A. So by now you must have understood what we have to do. We have to now imagine this entire cylinder or rod as a collection of infinite number of differential sections like this, or differential thin cylinders like this, which are kept in series combination with each other. This area is A. So there are infinite number of such differential sections, and they are all in series combination with each other because the heat is going through them like this. So the equivalent thermal resistance will become the summation of the resistances. So that will become integration of this. So this is summation by integration for the series combination of these sections. So that is integration of dx upon Ka from x equal to 0 to x equal to L. So that is integration of dx upon K naught 1 plus x by L into A from x equal to 0 to x equal to L. Okay. So now just complete this integration and find out how much is the thermal resistance. Yes, very good. It will come in log terms, but the value after putting the limits, Nikita, you still have to work that out. Okay, so this will be L ln 1 plus x by L, and on this we have to put the limits x equal to 0 to x equal to L. Okay, so integration of dx upon a plus bx is 1 upon b ln a plus bx. Okay, this is the indefinite integration we are using. So this is 1 upon 1 by L ln 1 plus x by L plus c. So that's how this becomes. So this is the indefinite integration. So now we substitute for the limits. So it is L upon k naught a. You can take this L outside into upper limit, that is ln 2 minus lower limit, which is ln 1, which is 0. Yes, very good, Jebel. That's correct. So we'll get the equivalent thermal resistance as L upon k naught a times ln 2. ln 2, you know, is approximately 0.693, almost zero point 0.7. So you can see in this question we have made use of the concept of combination of conductors, but instead of a simple combination of 2 or 3 or 4 or 5 conductors, we have actually have to take a differential element and combine it with other differential elements using integration. So it's a continuous distribution, so it has to be calculated using integration with limits. Okay, let's move on to another example, another type of example where we have to use integration. Next example is something where, okay, I'm okay. Okay, very good. So next up is a situation where we want to calculate thermal resistance for a conductor of non-uniform cross section, but isotropic. So it has a uniform thermal conductivity. So very good example of such a situation is frustum of a cone. That is, if we cut out portion of a cone such that we are left with a frustum kind of shape, and we want to make heat flow across the symmetry axis of this frustum. So this is a solid metallic frustrum. Okay. So you get a frustrum of a cone by taking an ordinary cone and then cutting out a portion of it. So this shape is called frustrum. Okay. This is the axis. So now suppose it has, this surface has a radius of small a. This surface has a radius of small b. Okay. And the length, the axial length, that is from one face to the other face, this perpendicular distance is L. And the solid metal has thermal conductivity K. So you want to find the thermal resistance for heat conduction along the axis. So again, you would have to insulate the outer curved surface and keep the two faces of radius A and radius B inside your two temperature reservoirs. So that's how you will achieve heat conduction along the axis of this frustrum. We want to find the thermal resistance. So now the problem is that we cannot use the direct formula L upon K into area because the area is not uniform at all points. So again, just like the previous problem, you have to slice it into segments or sections, and each section is a differential disk. But the difference is that K is common for all the disks because K is uniform. What is different is the area. Each disk has a different area according to its position inside the frustrum. So now try to figure out how we will do the integration. I'll show it to you in a minute. Try to figure it out yourself. Okay, so ultimately this type of problem is also about being able to handle substitution in integration, okay, and come up with a suitable method. So let's look at this in detail. Okay, so now at some distance x like this, we are slicing a thin disk. So like this. So more importantly, the radius of this disk is something that is going to be in between A and B. So we're going to have to learn how to express that radius as a function of this distance x. Because as heat is flowing like this, it's flowing through this conductor. Okay. So for this differential section, the thermal resistance is the length across which heat is flowing, which is the thickness dx, upon k into A. This. Now, so it all becomes about expressing r as a function of x, where r is some kind of function of x. So how do we understand that? Who can tell me what type of function of x is r? When we try to think that how to express r as a function of x, what type of function you think it should be? Just visualize how the radius is varying here with x, and you'll realize that it's varying in a linear fashion. As your x goes from 0 to L, your radius goes from A to B. So you can use the equation of straight line. Or geometrically, you can use similar triangles or something. So at some arbitrary distance x, sorry, arbitrary distance x down here, the value of your radius r, this will become a plus this slope, that is b minus a by l into x. This is like a y is equal to mx plus c type of function. Yeah, so like if you go by ratio and proportionality, it's like this, that x by l will be equal to r minus a upon b minus a. You can understand it by the slope method also. Okay, so anyway, now our net thermal resistance will have to be calculated by integration. Yes, yes, and K has to be there in the denominator, correct. Okay. So anyway, that K comes outside. The important thing is now we have to figure out how to do this substitution. So here we'll use a small trick. R is a lengthy linear function of x. So instead of substituting R in terms of x, what we'll do is we'll do this, take this equation and differentiate it. So dr by dx is b minus a by l. Okay, because a is a constant. So we can substitute dx as l upon b minus a times dr. So you can substitute this in the numerator. Okay. So next up, we substitute this here. So substitute the numerator instead of substituting the denominator, which will make life very lengthy. So in the numerator, substitute dx as L upon b minus a into dr by r square. And accordingly, the limits will change from limits of x to limits of r. When x is 0, the value of r is a. When x is L, the value of r is b, which you can see from this formula also. Or you can see in the graph that I've drawn above. So this becomes quite simple now really. It becomes L upon k pi b minus a. This also comes outside the integral. And now it's dr by r square, lower limit r equal to a to upper limit r equal to b, which is actually a very simple integration. So this is something we have to gradually learn with experience, how to substitute in a clever way so that the integration is easier to solve and not so lengthy. So ultimately, this is the thermal resistance that we get. So you don't have to memorize the formula in this or the previous question. You have to just know how to work out a question if we have this kind of variation. If the area of cross section is varying, or if the thermal conductivity is a function of x or something like this, then we have to slice it into differential elements and use definite integration. Okay, so there are also few examples of this type of integration applications in HC Verma as well as your module exercises for thermal conduction. So practice out some more questions of this type from that, and make sure you revise first law of thermodynamics applications, cyclic processes, heat engines, efficiency, and also the earlier part, calorimetry and thermal expansion, very carefully for the test coming up on Sunday. Next couple of days or so, you make sure that you keep your doubts noted down and keep referring to me by WhatsApp or in the mentorship sessions or whatever, whenever possible. Okay, and also do some revision of applications of work power energy from the previous chapter and friction and Newton's laws of motion examples. If you have completed HC Verma in your module exercises, then please do questions from DC Pandey in any of these chapters. DC Pandey is an excellent, you can directly do the JEE advanced level exercise from DC Pandey, that will help a lot. Okay. So anyway, that's it for today. Next week we'll be picking up radiation again from this point. We'll do some more practice examples of conduction, but mainly we'll move on to radiation, which will be the last part of heat and thermodynamics. So another couple of lectures and we are done with heat and thermodynamics. And yes, Aman, today's exercise, that is series parallel combination of thermal resistors and this application of integration of these two types, is also part of your syllabus. Thermal conduction is part of syllabus for Sunday's test. Okay, so wish you all
Sir,
the best.
actually, I had a doubt.
Yeah, beta.
Sir, actually, I got a book of DC Pandey for NEET from my friend. So,
Okay.
what would be the difference between the JEE book and the NEET book?
Uh,
Is it okay?
the NEET book will have less complexity of numerical problems. The conceptual problems will have the same difficulty level. But even for the JEE Mains, no, in comparison to NEET, you have more mathematical questions in JEE Mains, and in NEET you have more conceptual questions. So it's not going to give you the 100% same kind of practice that you require for JEE. You understanding my point, no, beta?
Yes, sir.
Also, the time frame of the exams is different. No? Like NEET, you have 60 questions and 1 hour. Like whereas JEE Mains, you have less number of questions. That means each question is more complicated. And JEE Advanced, even lesser questions, but there are so many different type of questions. More than one option questions, your column match questions, reading comprehension. So if you want to do proper JEE Mains and advanced exam, simulation type of tests, then questions, then you should refer to the JEE Mains and advanced version of DC Pandey. Okay, beta?
Okay, sir, got it.